Hi children. Last class we have discussed the solution chapter up to the colligative property. So today we are going to discuss what is colligative properties. Colligative properties, these are the properties of solution which depends only on the number of solute particles present in the solution and not on the nature of solute. For example, 1 mole of sugar and 1 mole of urea produce the same effect, but 1 mole of sodium chloride produces more effect because it dissociates into ions and increases the number of particles. So here one important thing is about non-volatile solute. What is non-volatile solute? A non-volatile solute is substance which does not evaporate easily and has negligible vapor pressure. When such a solute added to a solvent, there will be solvent molecule escapes there into vapor phase while the solute remains in liquid phase. This is the main reason why the colligative properties observing. So there are different types of colligative properties. First one, relative lowering of vapor pressure, elevation of boiling point, depression of freezing point, and osmotic pressure. First one, relative lowering of vapor pressure. In this, in a pure liquid, molecule escape from the surface and creates vapor pressure. When non-volatile solute is added, some of the surface is occupied by solute particles. So pure solvent molecules can escape. As a result, the vapor pressure of the solution becomes lower than that of a pure solvent. So the relative lowering of vapor pressure is given by the equation. What is the equation? The final equation is P naught minus Pa divided by P naught is equal to chi of solute. From this, we can understand the lowering of vapor pressures is directly and it is depending on the mole fraction of solute. So that's why it is a colligative property. So P naught is the vapor pressure of pure solvent and P is the vapor pressure of solution and chi is the mole fraction of solute. This shows that lowering of vapor pressure depends only on the number of solute particles. Next one, determination of molar mass. Using the relationship between, we can determine the molar mass of solute by substituting mole fraction in various terms. We get what M2 is equal to W2 into M1 divided by W1 into P naught minus P divided by P naught. Actually, you know that by the equation P naught A minus PA divided by P naught is equal to chi B. So chi B we can substitute into number of moles. So for the solute, number of moles is equal to NB by Na plus NB. So NB is greater less than Na. The equation tends to NB by Na. So you know what is Wa and what is Wb. The final equation we get for finding out Fb. So the molecular mass of solute then is equal to P naught A into Wb into Ma, P naught A minus Pa into Wa. You know all the each term that Mb is molecular mass of solute, Ma is molecular mass of solvent, Wb is weight of solute and Wa is weight of the solvent. P naught A is for pure solvent and Pa is the for the solution. So where M2 is the molar mass of solute, then M1 is the molar mass of solvent and W1 and W2 are mass of solvent and solute respectively. Then we are going to discuss the elevation of boiling point. So the boiling point occurs when the vapor pressure of liquid becomes equal to the atmospheric pressure. Since the vapor pressure of solution is lower due to the presence of non-volatile solute, you know that what is non-volatile solute. I have explained earlier. So the solution must be heated to higher temperature to reach the boiling point condition. Therefore, the boiling point of the solution is higher than that of pure solvent. So there is increasing in boiling point and it is called what? Elevation of boiling point and delta TB. We know that delta TB is equal to TB minus TB naught. TB naught for what? Pure solvent and TB for the solution, and when we comparing into a solid, we get a delta TB. So the delta TB is equal to TB minus TB naught. So the graph explains that if we draw a graph of vapor pressure versus temperature, the curve of the pure solvent lies above the curve of the solution. Pure solvent is lie above the solution and at the normal point there is TB naught. On the solvent reaches atmospheric pressure but the solution does not. The solvent reaches the atmospheric pressure, but the solution does not. The solution reaches this point at a higher temperature Tb. So the difference between these two temperatures is known as elevation in boiling point. So there is an equation for boiling point, that is delta what? The delta Tb is equal to kbm. That is, elevation of boiling point is directly proportional to what? Molality. Notice, not molarity, it is molality. So the kb is known as ebullioscopic constant. So then determination of molar mass. So by using different equation, we can find it out the mass of solute, that is m2 is equal to the equation, final equation. By substituting certain values, we get 1000 into W2 into KB divided by W1 into delta TB. You know that delta TB is equal to what? TB minus TB naught. So this is the main equation we are using for the such numerical questions. Then next, there is an application. Just go through it. It is seawater freeze at lower temperature than distilled water, but boils at higher temperature. Just go through it. Then we are going to discuss the determination of molar mass. I have told you earlier, there is an equation. You know that number of what delta Tb is equal to Kb in molality. Molality means number of moles of solute per kilogram or gram. If it is gram terms, then just multiply with 1000. Then we have to find out the moles of solute. The Wb by Mb is W by Mb, then M is equal to, we are substituting those values and we are putting into the delta Tb. Then we know that we have to find out the Mb, then hence the equation gets as Mb is equal to Kb into Wb into 1000 divided by delta Tb into Wa. So the molality, you know that what is molality, and just using the molality equation we are finding out the Mb here. Then we are going to discuss the depression of freezing point. The freezing point, the defreezing occurs when the vapor pressure of liquid and solid becomes equal. That means it occurs when the vapor pressure of liquid and solid becomes equal. Since the vapor pressure of solution is lower, this condition which is achieved at a lower temperature. Therefore, the freezing point of the solution is lower than that of solvent. That is showing in graph. So the decrease in freezing point is called depression of freezing point. It is given by what? Delta TF is equal to what? TF naught minus TF. So from the graph, we understand that in the graph, the vapor pressure versus the temperature has given. The freezing point of pure solvent appears at what? Higher temperature, while the freezing point of solution appears at lower temperature. The difference between these two showing as a depression in freezing point, that is delta TF is equal to TF naught minus TF. So here it is also directly proportional to what? Molality. It is also proportional to molality, and the relative lowering vapor pressure depends upon the mole fraction. Elevation in boiling point depends on molality, and the depression in freezing point also depends on molality. We know that delta TF directly proportional to molality. So change the proportionality constant. We are adding Kf here. Kf is known as cryoscopic constant. By using the determination of molar mass, by using this, you know that delta TF is equal to Kf into molality. You know the equation for the molality, number of solute divided by moles of mass of solvent in gram in 1000, and we have to find out the number of moles, that is why W by Mb is there. Then putting this equation into delta TF, we get the final equation as delta TF is equal to Kf into Wb into 1000 divided by Mb into Wa. A denote for solute and A denote for solvent and B is denote for solute. So from this we can find out the Mb by rearranging the equation. It comes here and it comes to this place as denominator. Then the Mb is equal to Kf into Wb into 1000 delta Tf into Wa. This is very important equation. Both are very important to find out the numericals for the solutions. So there is an application in cold climate. Ethylene glycol is added to water in the car radiator as antifreeze. During winter, salt is sprinkled on the road. Just go through the what applications. So thank you. In next class, we will discuss osmosis, osmotic pressure, and remaining topics.